couple of people pointed out that the last 2 minutes of the lecture last time, there was some weird video glitch in the video recording, so I'm going to go over this again with that in mind. So we discovered that there is a way to compute the force of kinetic friction when two surfaces are sliding against one another. There's two things you need to know, and only two things. The first, the one I discussed first, was the size of the normal force. So just how much is the normal force in this scenario? Because the normal force measures the contact force between the surfaces. It measures how hard they're pushed together. So how much friction you get when two surfaces slide across each other is dependent on how much contact force they have. You can increase it by increasing the contact force. This, by the way, is the first time where we've had that there's some mixing, quote unquote, of the x and y axes. So that something that happens on the y-axis, which is the contact force, can affect motion along the parallel surface, right? So how much force is applied perpendicularly between the surfaces affects the parallel force of friction along the surface. So that gives you a little hint of what's going to happen in these problem-solving strategies, is that we're going to have to, again, take something from the y-axis and put it in the x-axis. We did this commonly with time in the projectile motion problems, right? Where time can kind of be shared. Well, now we're going to have that in force problems where the normal force will be shared. We'll often compute the normal force on one axis and then plug it into the other, because the frictional force depends on it. The other thing here is called the coefficient of kinetic friction. It is a unitless quantity, and it must be unitless simply because it's the other quantities. Normal force is already a force, and then friction is another force. So there cannot be any additional units introduced by this coefficient. It is a unitless number, and it's basically an experimental measure of the roughness of the surfaces involved. So you know that it's not just about how hard the surfaces are pushed into contact with one another, but some materials are more, quote-unquote, slippery than others, right? So you have slippery things like ice and Teflon. You have rough things like kind of rough concrete or something like that. So that's our opportunity to work that into the formula. This measures the roughness of the surfaces involved. The larger the roughnesses of the surface, the larger this coefficient, the more the frictional force will be for the exact same contact force. Okay? So if a surface is rougher, then the mu k is a higher value. I already kind of slipped right there, so I guess I should make my point. It really does depend on both surfaces, right? It's not just are you sliding on concrete, but what is your object made out of, right? What is the bottom of the object? Is that slippery or not? But just to be lazy sometimes, I'll kind of conveniently forget that it's a property of not only the surface that you're on, but what the object surface is as well. So sometimes I'll just get lazy and I'll call it the roughness of the surface, okay? So that's just for being lazy. Both surfaces really matter. So think of this as kind of just a number that is like, it's like a power multiplier, right? It's just, here's the number that for this particular surface, this is the number I have to multiply the normal force by to get the frictional force. For instance, if you have a surface in which the force of kinetic friction is half of the contact force, right, then for that surface, mu k is 0.5. A surface has mu k of 0.5 when the frictional force is half of the contact force. You can have another surface where the force of kinetic friction is twice the contact force. So there are surfaces where the amount of friction you get is double the contact force between the objects and the surface. And then for that, mu k would be 2, right? These are just experimentally measured. Someone gets in a lab, measures the contact force, and measures the frictional force, takes the ratio of the two, and whatever that number is, that's what mu k is, okay? The common misconception, by the way, is that Mu k can range anywhere from 0, which is truly frictionless, right? You don't get any friction at all. And from there, of course, that's not realistic. There's no true surface that's truly frictionless. A lot of the surfaces happen to have values of mu k between 0 and 1. That's just a typical for real-world materials. And students actually get into this trap where they think that 1 is somehow the theoretical maximum. This is not like your coefficient of determination from your r-squared value from lab, where 1 is the best, right? 1 is perfectly linear. That's not what we have here. You can have very, very rough surfaces that have values of more than 1. There are surfaces that are approaching 2, okay? Now, is there a surface in the natural world where if you bring it into a lab and the coefficient of friction is 50, where the frictional force is 50 times the contact force? Not really, okay? So these are experimentally measured, and there's no inherent limit to the number. It's just what material can you drag up, okay? So these are just experimentally measured. In fact, what you guys will do as part of your lab on Friday or, Thursday, Friday, or Saturday, I guess, depending on which lab you're in. One of the things you'll do is you'll measure experimentally what your mu k is for your surface. So what is the roughness of your surface? The way you'll do it is to measure the contact force, measure the frictional force, and then divide the two. Okay? Does that make sense? That's how friction is determined. Okay? The one thing that is commonly pointed out, that seems like it's missing, is surface area, right? So you think, well, doesn't like the length and the width of the object matter for friction? It actually, to a very high degree of exactitude in the experiment, does not matter. So if you have an object that's like that, and you let it run against the surface, the amount of friction you're going to get is actually very similar to if you stand it upon end, right, with a much smaller surface area. So macroscopic surface area doesn't matter. So if you're wondering, don't we have to account for the length and width of the object in the equation? We don't. Surface area is actually already in here in a way that's perhaps unexpected. Microscopic surface area matters, and it's actually already in there. Let me explain. If you were to take out a microscope and watch an object sliding against the surface, you would actually see that they are not in contact everywhere. So if you took a microscope and zoom in here, what you would see is this. You'd have one object. Here's the surface that it's on. It's rough, so it's got these peaks and valleys. And then here's the object going across it. And what you notice is that they're not really touching everywhere. The friction comes from these certain points where they're interacting and other points where they're not really touching at all. These points, I guess I can mark them in green. They might look like this. I might kind of try to draw them. I don't know if that's clear. Draw the dimensions of my box. So I might draw where they're actually talking to each other, and that can be a much smaller percentage of the surface area than the actual whole, right? So they're talking in a number of different places, but not everywhere. The way that we increase where they're talking, right? So if we wanted to, for instance, get them to talk in a larger, more places, right? What we'd actually have to do is we'd have to press down like this, okay? I think it's like squeezing water out of a sponge, right? So what we're doing is we're trying to get more talk. So what we're trying to do is we're going to try to make it so that this surface talks in more places, right? That's right here, the size of the normal force. The whole reason why increasing the contact force is actually going to increase the friction is because it causes more microscopic communication. Does that make sense? So if you still don't believe me that the macroscopic surface area, length times width, matters, look at how your running shoes are designed. Okay? Your running shoes have treads. You don't have a maximum amount of rubber in contact with the road, right? That's not important. What's important is contact force, right? So if you step lightly on something, you might slip, right? But if you put more weight on it, more contact force, you're encouraging more microscopic communication, and you get more friction. Does that make sense? Okay, so that's pretty much it for kinetic friction. Just want to do a quick example problem to show you how you might execute on this, include it in a problem. And then I'll move on to static friction, which has a little bit more subtlety to it. So let's do an example. I have a flat surface, which is frictionless until we have a stretch of non-friction or not perfectly smooth material. And I'm going to have an object that slides on this. And I guess let me do this in terms of variables. So we have the givens. Let's say that we have the given of initial speed. And I have the coefficient of kinetic friction. So I have a sense of how rough that surface is. And let's go ahead and ask a question about this. How far does the object slide before it stops? And I guess I should clarify how far on the patch. So we'll start counting when it actually hits the friction patch. So that'll be enough information to do this. So this is a force problem, and so we can apply our six-step force problem-solving strategy. Step 1, object of interest. Pretty obvious, that sliding thing. 2, forces that act on it. Well, initially, when it's on the frictionless patch, there are only 2, and those 2 cancel, right? In fact, cutting to the chase, if I go ahead and set the y direction to be like, I guess I'll set the x and y like this. Here's the y-axis is upward, x-axis is forward. F net y equals may, yada, yada, yada. We're going to get n equals mg, okay? Is that okay? Or do I need to go through that? Okay. Now, if those are the only 2 forces on the part that's perfectly smooth, they cancel each other, what's the net force? 0. It's 0, which means that it'll just keep this velocity forever, right? That's Newton's first law, is that if you are left alone by the outside world, you just maintain the motion you already have. And so we can safely go over here to the beginning of the friction patch, giving it still the same exact initial velocity as we had over there. But now we're going to recap on the forces. Again, you still have a normal force, you still have gravity, they still cancel, so the n equals mg over there too, but now I'm going to have an additional force, which is kinetic friction. Which way does it act? It acts to the left. It always acts against your motion. Which, by the way, now that That's the only force left over after the other two kill each other. The kinetic friction force is the net force, right? So the net force and acceleration are going to be to the left. I guess I can draw that here. The net force and acceleration point to the left. There is no forward force. There is a forward velocity, but that's not a force, right? What happens when the acceleration and velocity are opposite? You slow down and eventually stop, right? So here's a common problem that students do. First of all, there is no forward force. There was maybe a forward force in the past sometime that got this started, but it's not there anymore. There is no forward force. What this thing has is its own inertia from wanting to keep doing what it's already doing, and now it's running into a friction patch where it has a single force pulling against it. And that's what's going to take away that motion. So again, velocity is not a force. Do not include velocity in your force balance. There is no forward force. There is only a backward force. And that backward force is what's going to cause you to slow down. So let's do the x equation. F net x equals max. I forget what step this is on, so I think this is step 5 now. So let me just recap. Object of interest, step 1. Step 2, forces. Did that. Step 3, decide on x and y axes. How do you do that? Well, you want to put one of your axes along the acceleration, right? So I know the acceleration is going to be horizontal, so I put x as horizontal, right? Now, if it bothers you that the plus x direction is to the right while the acceleration is to the left, no biggie, right? It's going to be a negative acceleration, but it's still only all x, right? It has no y acceleration. Okay, the y acceleration is 0. Step 4 is to break forces into components. I don't have any of that to do. There's no forces that are diagonal, right? They're all along one of my axes. In this case, moving on to the next step where I plug in, I have the force of kinetic friction, which acts to the left. So remember, this part is just the size, and so I do need a negative to indicate that it is to the left. And that is going to be the sole driver of the acceleration, or in this case, of course, since the acceleration is going to be opposite the motion, we might call it deceleration if you so choose to want to do. So now we can use our formula. Our force of friction, we decided it's in the negative direction. We have a rule of thumb for figuring out how much it is. And of course, this is what I was talking about earlier. How do we figure out the contact force here that's going to figure on this, tell us how much force acts in the minus x direction? Where do we get that from? So the frictional force acts to the left, but it depends on a force which points vertically. So we need to steal this and put it in here. So we get minus mu k mg. And then here, the mass cancels. So if you were at this point kind of stressing out over the fact that I didn't give you the mass, that's why doing things symbolically is so great, because you will find that things that you might think you need, you really don't. So I've figured out the acceleration. Now that's not what I really want. I want how far does the object slide before it stops. Now, of course, if I want to figure out how far it slides, how much or how little acceleration it has is going to determine that. So this is an example where I wanted to show you that once you've used forces to calculate an acceleration, you can now go ahead and use your constant acceleration stuff from earlier homework. So it's a nice 1-2 punch. I might go ahead and put down my 5 variables in no particular order. And I know that mu k g in the negative x direction is going to be my acceleration. My initial velocity I have, I'm going to call it plus v initial. So remember when you're doing this to put signs, right? So in my case, anything that points to the right is plus. Anything that points to the left is negative. Of course, what am I looking for? Displacement, right? How far do I slide on this patch before I stop? And of course, I need three things to get a fourth. So what's the other thing I know? V final is 0. Don't know, don't care about the time, right? And that's going to help me with my equation selection. Just out of curiosity, does anyone remember which one's missing time? Not the second one? Third one. Yes, that's right. So let's do it. What? Question? No? No. Question? No. So it's going to look like this. Is there a question? No? Okay, so we'll plug in 0. 0 squared is still 0. V initial squared plus 2 negative mu kg delta x. And remember, we're solving for delta x. So delta x, in terms of givens, is here. This is, again, not a derivation. This is an example. And just checking the rules of the game, the equation is in terms of things that I'm given, v initial and mu k, and g is always allowed. Okay? Let's just double check it, give it a spin, okay? Let's make sure that the proportionalities are right. So first of all, according to this equation, if you hit the friction patch going faster, should you slide further or shorter distance? Further. Is this equation, does it bear that out? Yeah, it does. In fact, it tells us that if we double the initial speed, what actually happens to the distance you slide? Nope. Quadruples, right? Delta x is proportional to v squared. So you actually slide 4 times further. Proportionalities, they're useful, right? Now, if you made the surface rougher, should the object slide further or less far? Less far. Does the equation bear that out? It does, right? Because this is in the denominator. You make that bigger, you make this smaller. In fact, it tells us that if it's twice as rough, how much will it slide differently? Half. Okay? So what I'm basically saying is that delta x is proportional to v initial squared. That was the first one, and the other one, delta x is proportional to 1 over mu k. So that is some insight that you can get from symbolic solutions. You can double check that everything is where it should be. Are there any questions on this before I move forward? Yeah. What about it? Well, remember the 2 is going to be part of the formula for the first one and the second one, so it washes out. So if you need to revisit from the first homework why these factors don't matter, that's a good thing to do. Or we can do that in office hours if you want. Okay, any other questions on this before I move on to static friction? Okay, so let's talk about static friction. static friction, as you have on that chart from last time, the value for the static frictional force can vary anywhere from 0 up to a maximum of this. So this is the maximum value. Now, as far as how to compute that maximum value that it could be, you notice that it's a very similar features, right? You have n, which again is not newtons, it's not a unit. It is the size of the normal force. So it depends on the size of the normal force. There's also a coefficient of friction, now called the coefficient of static friction, not surprisingly, hopefully. So in order to compute the maximum, it's very similar. Okay? So what I'm going to focus on here is what is the deal with this range. Okay? How can a force now have a range from 0 up to a value that, and then of course that being the maximum, it can't go past. Now where are you in the range? As needed. Okay? And I'm going to explain that here in just momentarily what I mean by that. But I should point out that this is not the first force that has been acting on an as-needed basis. It's actually the third one. One of the forces we talked about acting on an as-needed basis was the normal force, right? Normal force protects the structural integrity of a surface. So if I push 1 Newton into a surface, it pushes 1 Newton back, right? If I push 2 Newtons in, it pushes 2 Newtons back. The only difference of this is that normal force we didn't say had an upper limit, right? So for us, if we have 1,000 newtons acting into the surface, normal force pushes 1,000 newtons back. It's variable, but without any kind of range for how much it could be in reality. Okay? Now, of course, in the real world, if I push hard enough on this table, I'm going to break it. So there is some upper limit. Okay? Another example we had of a force that kind of does what is needed is tension. You can have a rope that is very loose or very tight. It just depends on what it's being asked to do. So it varied necessarily according to the situation. Now, again, we didn't specify any upper limit. So our strings are infinitely strong. We just said if it needs to maintain this amount of tension, it will. Again, in reality, of course, eventually if you pull something hard enough, a rope will snap, right? Here we have to acknowledge that static friction does something on an as-needed basis, but it would be silly to say that we're not going to acknowledge that there is an upper limit. Okay? So to give you an example, let's just suppose, just so I don't have to keep saying mu sub s times n, we're going to suppose that we calculated this in a particular situation to be 5 newtons. Okay? So I'm not saying it's 5 newtons in every problem, but I'm saying, let's say we find it's 5 newtons. That means that the force can be anywhere from 0 to 5. Okay? So let me have an object. This object is at rest. That's, of course, static friction. Is the kind of friction that prevents you from moving something. And over here on the right, I'm going to put various pushing forces that I'm going to use to attempt to move it. And on the left, I'm going to catalog the frictional forces that are going to hold me back. So I'm going to not push on it. 0 newtons. So I guess let me list them down here. 0 newtons. Okay? My table right here, I can pull this up here and use it. If I don't try to push it forward, how much does static friction need to exert to keep it from moving? Doesn't need to do anything. I'm not asking it to do anything. So if I don't push on it, static frictional force is not 5, it's 0, right? Now if I push on it with 1 newton, right? I'm pushing forward 1 newton, okay? But it doesn't move. So how much does static friction have to hold back? 5? 1 Newton. That's all it needs to do. It could be 5. It doesn't need to be 5 because I'm only pushing 1 Newton, right? So if I exert 1 Newton, static friction needs to exert 1 Newton back. What if I push with 3 Newtons? Is it going to move? No. Because if I push with 3 Newtons, how much does static friction hold back? Is it 5? No, it's 3. Okay? So it's on an as-needed basis. It's just like a rope that's supporting the amount of tension that's necessary, or normal force canceling off forces necessary to prevent a surface from getting crushed. So when I say as needed, I mean as needed to prevent motion along the surface. So basically, I can infer the frictional force, as I've just been doing in this problem, by knowing that the frictional force has to equal any and all forces that are parallel to the surface trying to move it. Same size, of course, opposite in direction. So for instance, if I have 17 different forces acting on an object, and those 17 different forces, either their entire force or components are parallel to the surface, and those add up to 4 newtons forward. Oops, should draw that longer. How much does static friction have to exert to keep that object in place? Is it 5? It's 4. So I think a lot of times students just gravitate to they just see a formula and they just want to shove it in there. I want to use this, right? You want to use this at all costs without actually thinking about the situation. Let me ask you this. If you only tried to push forward with 1 Newton and there were 5 newtons back, what would happen? It would come toward you. You push something and it comes toward you. That doesn't make any sense, okay? There are only 2 options for this. Either it doesn't move or it moves forward when I push forward on it, right? It's not going to come back at me. So be very careful to not plug in this unless you have some reason to believe that static friction actually has to be maxed out. In my situation, I would have to push forward with 5 newtons if I wanted to actually have that this force be 5 newtons. Okay? Static frictional force is only going to exert its maximum force if there's any reason for that. Okay? So in all of these cases, what is the net force? 0. The net force is 0, and since the net force is 0, it stays at rest. That's because the static frictional force is successfully canceling off one or more forces that are trying to move it. Now here's where the difference comes in, where we treat static friction on a different level than normal force or tension, is that we know in the real world that surfaces break, so there's an upper limit to normal force. We know that ropes snap, there's an upper limit to tension, but we don't necessarily worry about it. It's not a big deal to say, okay, we're going to have these strings that are very strong and surfaces that are very strong. We don't have to worry about the upper limit for those forces. But how weird would it be to claim that this thing could never move? Okay? We obviously have to have an upper limit to static friction, because if we push harder than that, we can actually get an object going. So we have to acknowledge the fact that there is an upper limit to this, and if you push harder than that, then static friction can't cancel you and you will move. So if you push with 5.000001 Newton, just a smidge more, then you will not stay in place, right? You will then be in motion, and you should actually switch to using kinetic friction at that point, okay? So any pushing force that is greater than 5 newtons in this case, the object will move. And what we use kinetic friction instead. Okay? Now, if that seems weird and hypocritical, that what do you mean? Shouldn't we use static friction first and then kinetic friction? Well, this is where we have to play around a little bit with the fact that it's really one friction. There's friction comes as a two-pronged attack, and you have to choose which one you're going to use. If something slides, it starts to slide. Even if it slides from rest, you should use kinetic friction. Static friction is really only for things that don't move. Okay? So I'll come back to that later and talk about kind of comparing and contrasting the two types of frictions. But for right now, what I want to do is I want to do an example problem with static friction. Okay? And I should mention that there are several problems on the homework which are meant to make you fully realize what this statement implies. Where you will be asked to find the force of friction, and it's somewhere between 0 and the maximum as needed. Okay? So to really hammer that point home, to try to prevent you from always plugging in this value when it's not warranted. Okay? So let's do my example. We're going to go back to the inclined plane. So here my givens are going to be, let me give you theta, and let me give you the mu sub s and the mass. So this is now an inclined plane that isn't perfectly smooth. It is rough. And the way we use to rate that roughness, if it's not actually moving, I guess I can write that. This thing is going to stay at rest. The roughness rating we need is the static coefficient. Here's what I'm going to ask. I want to ask, find what is the force of static friction at as a function of theta at a given theta at which it will stay at rest. So which it stays at rest. And then I'll give you a specific number to plug in, just to make it easier to kind of have a discussion. For the sake of plugging in numbers, I want to plug in that the mass is 10 kilograms. The theta is going to be, let's make it 20 degrees. And the mu sub s is going to be 0.8. So that's going to be my numbers for part A. And then for part B, I'm going to ask, what is theta max? I'm basically going to ask, if it's not 20 degrees, what is the largest angle at which I can hope this object to stay at rest? Okay. So first, what's the force of friction? Static friction when the angle is 20 degrees. And secondly, how much more could I tilt this thing up before the thing couldn't stay in place anymore? So let's try it. I'm not going to finish this today, but I'll finish it on Friday. Step 1, object of interest. Obviously, it's that block. Step 2, forces that act. Well, we have a previous experience with an inclined plane, normal force, force of gravity. We've discussed the situation at length. What happens? Well, We know that the normal force cancels with one component of gravity, and the other component of gravity, which is parallel to the surface, is what causes it to slide. But then the static friction force in this case says, nope, you are not going to slide down. It acts opposite the way it would slide. All right, those are our forces. Let's pick an x and y axis. I'm going to pick this. Same as before, parallel and perpendicular to the surface. I don't technically have to pick that because the reason I did it before was the acceleration was going to be in the x, right? And so there I want to pick one of my axes along the acceleration. Here I won't have any acceleration, right? It's just going to stay at rest. But that's still the best choice. It's still the best choice for axes because then two of my three forces lie along them and I only have to SOHCAHTOA one of them, right? So I'll do my force of gravity components like I did before. Let me draw my free body diagram. Here are my hopefully familiar components of the force of gravity. That's the same as the inclined plane problem from before. I still have a normal force, but now I also have a static frictional force. Good free body diagram pretty much tells you what's going to happen. These two forces have to cancel regardless, right? Whether or not you're sliding or not, you can't go into the surface. So what comes out of the y direction, yada, 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 we're going to get this. And again, if you don't remember how that goes, it's the same as the frictionless inclined plane. So it's in your notes. The only difference now is in the x direction. Before, mg sine theta was free to do its thing, right? That was the net force that caused the acceleration, but now that gets killed. And of course, if those forces all cancel, then the net force is 0. It'll stay at rest like it was before. So in the x direction, here's what we have. The x acceleration is 0, 2 now, just like the y one was. We have plus mg sine theta, which is going to be canceled off by the force of static friction. So what do we get? This is the force of static friction. That's its job, right? What's trying to move it? Mg sine theta, right? It's not a pushing force now. It's mg sine theta that's trying to move it. Well, how big is mg sine theta? Mg sine theta is, if I can compute this correctly, 34 newtons. That's as needed. Okay? That's how much force is needed to hold this thing back. 34 newtons wants to get it going. So static friction says no. I want to point out that the maximum static frictional force in this situation, of course, you can use that formula like this. You can plug in what the normal force is, and I'm here to tell you that that force comes out to be 74 newtons. So which is the answer? Is it 34 or 74? It's the 34. What we've just computed here is we've shown that the static frictional force could be anywhere from 0 up to 74, but we don't need all 74 because there's only 34 trying to move it. So this is again a situation where you have no business assuming that you need the very most that static friction could do when you only have 34 that's even trying. So again, if you push something forward with 34 newtons, 74 isn't going to be back at you. That would mean it come toward you. mg sine theta is trying to get it moving with 34 newtons, and it does not need to be 74 back. It needs to be just 34, okay? So this is correct. The fact that you have up to 74 actually means that you could push it downhill and it still wouldn't move, right? We found that this was 34 newtons. How much more force could I push on this before, and it still wouldn't move? I could push another 40 downhill and it still wouldn't move, because in the bank, static friction has up to 74 newtons of fight. But you don't need all 74 newtons of fight in this situation, okay? So that's part A, and we'll use these equations right here to find the maximum angle. And of course, the way we're going to find the maximum angle is by saying that the actual amount of force you do have is going to be the maximum, right? So you tilt it up to an angle such that mg sine theta is going to ask for every little last drop of what this can do, okay? So that's the strategy in part B. The whole definition of theta going to theta max is that the force of friction will finally grow to its maximum value to stop the thing from sliding. So I'll complete that on Friday.